So I've got this direct drive motor, and as I try to turn the shaft, I can feel like, I don't know, there's like a viscosity pushing back. I mean, there's some friction to get it going, but there's kind of like, I don't think it's necessarily static versus dynamic friction. It seems like the faster I spin it, the more current I need. So if we take a look at viscosity, if it's very thin like air, it flows quickly. If it's thick and goopy like peanut butter, it's a little thicker. So as the viscosity goes up, you need more torque to overcome it, and you need to apply more current. And so this brings us to a question of, what is this VcFF, velocity current feed forward? So to overcome the viscosity, we would need to apply a current based on the command for velocity. So output over input, current out over velocity in units of, well, current in amps and velocity in RPM or whatever the units are that you use. So in the drive, we're using counts per cycle. This drive is a plus drive with an FPGA, so it has a 250 microsecond update rate or cycle, so many counts per cycle. And then on the next page, we've got the A to D units for the current command, and that's a little trickier. How do we zoom into this thing here? Just use the mouse. Whoa! All right, I'm gonna edit. All right, let's just, oh, there we go. So there's a parameter 0x84, gives the drive's current in units of 0.1 amps, corresponding to the A to D maximum reading, and it's a 16-bit value. And anyways, you can determine what the A to D units are for the current. That's a little more accurate than what's the drive's peak current, because it's plus or minus peak for full scale, and maybe a little bit more so that in case there's some overshoot. So those are the A to D units. Anyways, for controllability, we're going to look at the torque control, and this is a presentation by the professor of Northwestern, Kevin here, and there's a term, he drops the integral term, but there's a term for the velocity times a constant. So let's see what he has to say.
Makes each joint have the same stable linear aerodynamics.
Oh.
This is a block diagram of the computed torque controller.
Yeah, the nice block diagram is your PID controller, but here you've got your torque output. This is torque current to the motor, and here we're measuring the velocity, and this is the angular velocity, or velocity goes through the PID. So the angle and the rate of change of angle, the dot, and so the dot angle, it's the velocity, right? So the velocity, there's viscous in the system, there's a constant times that, and it goes to the summing junction to produce a torque. And really, that's all we're trying to do is tune the VcFF. We don't just set it to 16,384 or 32. We tune it such that at that speed, we're going to get a certain amount of current. And so what I did originally, yes, 32 is 100%, but what does that mean, right? It's a value that you're supposed to tune this so that the speed times this value equals the current required. And so I tested the motor. In a current mode, I just commanded some current, like I did 0.5 amps, and then 1.5, and 2. And I can see the velocity would increase as my current went up. And so I could plot. Now, the other thing you could do is, while you're jogging it, you could look at the current to see what the current is when you're jogging it. And And that's what your goal is for tuning this value. And the method I'm using here is like a superposition. So I turn my gains off for VP and VI, and I want to produce, for a commanded speed, I want to get that speed just by commanding torque. So no PID, pure open loop. It's a dynamic model tuning, and we can take a look at that on the scope. So here's my scope trace, and so I got this limited velocity is what I'm going to command. The actual motor velocity is what comes of it, and the actual current is the current required to produce this speed, given this viscosity in this system. Of course, the commanded current is perfect, and the actual current just looks a little noisy because of the samples and whatnot. But I'm not going so fast. I'm not velocity limit, voltage limited, or no voltage limit, no current limit. So you got to go slow enough. You can test it at different speeds and stuff too. So just basically, I'm going to jog it, and it's going to record the data. You can see the current that I get when I command. Well, I'm not really getting 600 RPM here, am I? So let's check the gain again. So let's see what it gave me. See, the speed is low here. I don't know, maybe it warmed up or something and it's a little bit different. So this might overdo it. So I'm cranking up the gain. Oh, I think that overdid it. Yeah, I'm going 1,000 RPM. Let's do 1,500. It's a little bit subjective, but not really. It's just science. So, the dynamic model changes based on temperatures and whatnot. A little bit of continuing to increase velocity too. I think that's getting pretty close to it. Yeah, 400 RPM. Let's try a little bit more. And so have the scope on 12 seconds of trace time. So I'm starting to pull in a little bit. So you don't want to put too fine a shine on it. Just find a value that gives you some compensation for the viscosity. Slower speeds, maybe higher speed. There may be some differences in the system that viscosity may not be constant here. It may be more like dynamic or static friction, but you get the idea. I'm getting some measure of speed control by compensating for the viscosity. Not perfectly linear, but very helpful in the system. So a combination of this and some PID tuning. So in a way, this is kind of bypassing the velocity loop by applying a current. Haven't tested it near zero, but this flow speed seems to work. As long as we can still get full range of control at the output. This is a method for using the velocity current feed forward. So yeah, you can see it near zero. It didn't overcome the static friction, but once I get it moving, then it's just viscosity. So that's static friction would be a different story. So back to the practical application would be to put it in a position mode and tune up the PID rather than just the velocity loop surrounded by a position loop without the integrals and derivative terms. So I've got a PID here now, and so I'm going to try to jog it in a position mode. And looks like I'm going to have to do some tuning on that. That's a little bit of a bumpy ride. So what happens if I over integrate it? Oh, that's not good. Oh, yeah. Overdid the current. And then there's a D term, so you could put a little D term in there. And again, now we're tuning up a PID, so a little bit different philosophy on tuning than a nested loop. But there you go. It falls into the classical model of PID tuning, and we should get some pretty steady control. Yeah, it's a little spongier. I'm not sure. It usually takes a while to tune a PID. You got to do sort of a round robin method for P, I, and D. And I'm going to leave it at that. The purpose of this video was to talk about the velocity current feed forward. And one thing you could do is completely bypass the velocity loop. On the other hand, inner velocity loop does provide some nice stability. So I'm gonna keep that velocity loop tuned here, and hopefully just this feed forward term will assist us in the system when viscosity becomes an issue. Okay, thanks for watching.